Hey, this is section 1.7, real-time computing. I'm Picone Garbinian Divine. Helped me write this book on real-time computing. Check it out at the MIT Press website and at the companion website, rtcbook.org. Introducing real-time computing. The mechanical engineer, who this book is specifically geared toward, is especially interested in the three types of computing that follow. 1. Scientific computing. The solution of mathematical models of phenomena. Languages MATLAB and Python are the most popular. 2. CAD, computer-aided design. Three-dimensional drafting, finite element analysis, and computational fluid dynamics. Tools like Inventor and ANSYS are examples. 3. Real-time computing. That's what we're doing. Computing that must interact with its environment, which has its own dynamics. This environment is usually electronic, and it is often also mechanical. For instance, a mechanical control objective and an electronic interface. Events in these dynamic systems unfold in real time, described by the time variable in dynamic equation models. From the mechanical engineering perspective, a dynamic system interacts with a real-time computer via input and output. That is, a real-time computer is an element of a dynamic system. Physics-based mathematical models are often used to describe the dynamics of electrical and mechanical systems. Although a computer is fundamentally an electronic system, the complexity of computer systems precludes modeling them as electronic for the purposes of dynamic system models. It's too complex. A real-time computing system can be treated as though it has its own dynamic model that describes how an input relates to an output. So let's model real-time computers. Dynamic system modeling of real-time computers is challenging because of nonlinearity and complexity. The operation of computer components is highly nonlinear by design. The transistor is the fundamental building block of processors, but it is a nonlinear element, and a single processor may contain billions of transistors. It is intractable to model the state of every transistor in a processor. Computational systems require unique considerations, especially with regard to real time. The primary activity that takes time in a computer is processing, logical, arithmetical, and similar operations on data. Thus far, in this chapter, we have explored the structure and operation of computers. Now we consider some basic modeling of how real-time computers work. A real-time computer has some number of tasks to process. A task has two primary constraints. 1, precedence relations, which require that certain other tasks are processed before the given task. And 2, real-time deadlines by which the task must be completed. Okay? Deadlines and precedence relations. How can we design to meet deadline constraints? This is a special type of scheduling problem, scheduling real-time tasks. A schedule is a set S of sequences of tasks, one sequence for each processor that includes all tasks. For a single processor and tasks A, B, C, a schedule would have a single sequence, A, B, C, or B, A, C, or some other permutation. A schedule is incorrect if it violates precedence relations. For example, if task A is a precedent of task B, a schedule with sequence B, then later A, would be incorrect. Precedence relations are part of the conventional scheduling problem, which usually attempts to minimize the total time for all scheduled tasks. Something unconventional about real-time scheduling problems is the additional deadline constraint. A task must have a real-time deadline. So a schedule can be incorrect by violating a deadline. So here's an example of a real-time schedule So consider the tasks A, B, C, D, E, and F with execution times and precedence shown in the upper figure, and with deadlines for E and F of 31 and 48 milliseconds, respectively. So here they are, A, B, C, D, E, F. The precedence relations are shown with the arrows, so A has to precede E, and B has to precede E. C has to precede D, which has to precede F. And the amount of time in milliseconds that each task takes is given next to the circle. So 20 milliseconds for task A, 10 milliseconds for task B, etc. Good. Given a 2-processor real-time computer, there are many possible, if potentially incorrect, schedules. The lower figure shows 2 such schedules, S1 and S2. Here, S is correct in terms of precedence relations, but incorrect in terms of the task E deadline. So if we look closer at schedule 1, we see that we'll have our 2 processors working on A and C, and then B and D, and then E and F, which actually is okay in terms of precedence relations. So A precedes E and F, A precedes E and F, B precedes E, B precedes E, C precedes D precedes F, C, D, F. And we see that we keep both processors busy the whole time, which in conventional computing is ideal. We have them both working, and we have a nice balanced load here. So 35 milliseconds to get all of them done. So this would be probably an optimal schedule in conventional computing. However, in real-time computing, it is incorrect because E has to be finished in 31 milliseconds. So here is E's deadline, 31 milliseconds. And we see that E is begun, but it has not completed yet. So it completes in 35 milliseconds. So it misses the mark by 4 milliseconds. The total processing time is worse for schedule S2. However, the deadline for task E is satisfied, as is that of task F. So here we do A then E on one processor. So A then E, okay. A precedes E and F. So E and F, that's good. B precedes E and F. B precedes E and F. C precedes D precedes F. C precedes D precedes F. So all the precedence relations are satisfied by this schedule. E completes before the E deadline, and F completes before the F deadline. So this is a correct schedule for real-time computing purposes with the deadline constraints. Schedules are optimized systematically by a task scheduler of a real-time operating system. Designers can influence the scheduler in ways we will explore later in the course. Okay, qualities of tasks and deadlines. Periodic tasks. These are repeated in regular intervals, periodic. Often they are time critical. Periodic tasks are important for feedback control systems because the sample rate is often fixed and our assumptions about the performance of the control system depend on that periodic update of the control law. For example, a self-driving vehicle updating the angle of its front wheels. We're going to need to do that at well-defined intervals in order to guarantee safety. Aperiodic tasks arise only when a specific event occurs. They're often less time critical than periodic tasks, but must be processed in some reasonable amount of time. We can't put it off indefinitely. For example, a passenger in a self-driving vehicle presses a button to increase the fan speed of the air conditioning. That would not be as time critical as updating the control law that we saw above for the angle of its front wheels. But we do need to get to it eventually. Some aperiodic tasks are time critical, such as an object avoidance control system on the same vehicle. So just because it's aperiodic doesn't mean that it's not time critical, but many aperiodic tasks are not as important as the periodic tasks, like the control law update. Task priority by deadline quality. So we like to speak of hard deadlines for which catastrophic failure would occur if the deadline is missed. So we're talking damage to equipment, the system going offline, breaking, potentially injury, humans being injured, that type of thing. So catastrophic failure if missed. Those are hard deadlines. For a firm deadline, the task is no longer relevant after a certain deadline. So there's sort of like a cutoff, and then if we haven't done this task by then, we'll toss it out. And then soft deadlines, where the utility decays after the deadline but remains useful for some time. For example, a hard deadline would be one for airbag deployment. We have to deploy that airbag within a certain amount of time, or there could be an injury resulting. An example of a firm deadline would be like a power conservation for a laptop. Maybe the screen would dim after a certain amount of time of inactivity. But if someone has plugged in the device, in the meantime, then it becomes irrelevant to start to dim the screen. A soft deadline would be something like in data logging, where the data is still useful after the deadline, but its value decreases over time. Predictability and fault tolerance. Every design includes uncertainty due to the complexity of every real system and environment. When a real-time computer is in the system, this complexity and therefore uncertainty can increase. It is the designer's responsibility to quantify and minimize prediction uncertainty. This is typically accomplished through a combination of the following: theoretical models, testing, iteration on the design, and redundancy. A fault is when a task fails. Sometimes a fault is just a failure of communication with a component of the system. That happens a lot. Fault tolerance, the ability of a system to recover from a fault. In real-time computing, the time needed to recover from a fault can be catastrophic, especially when there are hard deadlines. Fault tolerance should be considered for determining if a schedule is correct. The probability of a fault for a task should be part of the scheduling problem. So if there's a high probability of a fault, we need to have time to recover from that fault built into the schedule. For tasks with hard deadlines, it should be possible to recover from faults without missing deadlines. Okay. So that's all I've got for you here. We've gone from general computing. Now we've taken a look at real-time computing and how it relates to the general computing environment that we've discussed so far. And we've got a few more sections left in this chapter. So I'll see you next time.